Hello, everyone. Thanks for coming to this session. So in this session, I'm going to talk about this IBM Bayesian Optimization Accelerator. This is a new offering from IBM, started from this year. And I think there's a new release coming soon at the end of this year. So in this talk, I'm going to talk about this architecture, the interface, and some initial performance using this accelerator as comparing with some other methods. So what is this Bayesian optimization accelerator? To simply put, it is an optimization toolkit which helps solving the optimization problem. So you have engineering problem and which has tons of parameters. You want to figure out what's the optimal solution to your engineering or to your design issue. So this is a toolkit which will help you to get that done in as few steps as possible. And from the architectural perspective, this is an IBM appliance which consists of AC922 with Red Hat Enterprise. So it is pre-installed with the BOA software, and it can be easily hooked up to any existing computing environment. So the BOA appliance itself is a power box running Linux with BOA services, but it can be hooked up to like Power x86 and ARM and any operating systems as well, because the communication down there is through the HTTP and it's very minimal communications. So this finding those optimal solution, this is a long time challenging problems in the field, and there are so many other methods out there, but many of them, they may have their area where they would be doing a good job there, but for this particular problem where the Bayesian optimization is focusing on, we're trying to optimize some functions which doesn't have the derivatives. Also, it may not even have analytic forms. So says, for example, you're doing some machine learning thing. What you have is just some data. So you have the condition you get the data and your data points there. So you don't have any functions at all. And also the problem may have multiple minima or maxima. So it depends on which one are you looking for. And the data may be noisy. So, and the last but not least is that the function can be very expensive to calculate. So you want to get this done in as few as possible number of steps. The many other methods listed on the bottom left here, it has their limitations. So in terms of those efficiency, so Bayesian optimization, which has some intelligence algorithms built in, it can do those intelligent optimization so that the work can be done in less number of steps. So how Bayesian optimization works to say optimize a black box function, because we don't know anything about the function. We only know its values and some input parameters. So it uses a surrogate function to represent a black box function. It's similar to, say, people are familiar with those regression or those like least square fittings there. So this surrogate function is your phased function to represent this black box function. But because the Bayesian optimization uses a probabilistic model, so that means with your regression, in addition to get those regression which represents the real function, it also have some statistical range for your regression, say the standard deviations. So which tells you how likely the or how close your regression is to your target there. So the Bayesian optimization can make use of those facts and to come up with some smart way to figure out what your next sampling point would be. So this is achieved by using yet another kind of function, which is called the acquisition function. So the acquisition function, its purpose is to get a next sampling point. And to use this, so the acquisition function will explore those surrogate function behavior and together with its own purpose to find out the next point to do. So we are actually trying to transfer one kind of optimization to another one. So this acquisition function itself, you need to find the maximum of this acquisition function. But the good thing is that the acquisition function is chosen to be very cheap to optimize. So that it takes so much less amount of effort to find the optimal solutions. And over the years, there's lots of studies and choices. So the IBM's Bayesian optimization algorithm implemented many of them, and it has its own additions. So makes it more versatile to be able to tackle a broader range of problems. So with those probabilistic modeling and those acquisition function, that's why the Bayesian optimization can get the work done in less number of iterations. So here are some kind of acquisition functions out in the field. There's upper bound confidence, the probability of improvement, and expected improvement. So the key role of this acquisition function is to, well, first is to cheap to optimize, and then second, also important, is to balance the exploration and the exploitation. So that you don't stick to like some local minima if because you are trying to also explore. And also, if you are doing too much explorations, you may be very slow to convergence. So that a fine tune between those two areas is also a key to the success of the Bayesian optimization. The process for this Bayesian optimization works is you establish a probabilistic regression model. You typically use Gaussian processes and initialize with a few data points. Then you calculate the posterior distribution, which is a surrogate function. And then you calculate the acquisition function to get those recommendations for the next sampling point. And then you use those new sampling point to get the objective function. And then, so this is an iterative process. The process will end, say, until your budget runs out or you achieve the required accuracy. So to illustrate this whole process, we use some very simple function which has an analytic form there. So this is actually a one-dimensional problem there. Actually, Bayesian optimization can handle multiple dimension problems. So here, to use example, we just use a simple thing. So we know for this function, our target is to find the minimum. So here we know the minimum is close to the point, like 0.3, minus 0.3. And this chart shows the progression of the Bayesian iterations. So the left side is the surrogate function at the end of each iteration. So there's those red dashes is the true function, which we are trying to find its global minimum. And the dashed green is the surrogate function, which is used to represent this true function. And the red, the red dots are the sampling points. And the green shaded area is the uncertainty of the surrogate function. So which is simply the standard deviations. The right-hand side is the corresponding acquisition function and the next point to sampling. So it's the blue dot is the next one, which the algorithm is going to do the sampling. So for this first iteration, we use the 2 points, random points to start, to initialize, and then it tells us the next point to sample is this one, so it's close to 0. So we come to the next iteration, it will get the surrogate function at this point, and then we calculate the acquisition. So the recommendation is here, so it comes this. So as more and more points are calculated, our model, this surrogate function, the dashed green line, will be more and more like those true functions. So we can tell this progressive progress here. This one just continues with the previous chart. So it goes from iteration 6 to 10. So we can tell at the end of 10, it's pretty much find out the global minimum. And there are those areas which is still largely not explored because the algorithm is not interested in getting the data points across. It's focusing on finding those minimum. Yeah. So this chart shows the final results after 15 iterations. So again, the left one is the same as before. This one is a convergence plot. So it shows you the how good, how best the results it be after each iterations. So from here we can tell that those 2 points are those random, and then the third one is not improving that much, and then it improves a lot here. So by the iterations of 7, it's pretty close to what the optimal would be. So this is enough, for this Bayesian process. This shows, how quickly it can get to those the converge points there. And this chart again, it shows the structure of the BOA. So the left side is the BOA server, and then the right one, say here are the scheduler input data. Those are your existing computing environments. So you don't need to change anything from your existing compute environment to be able to use BOA. What you need to do is to just have this BOA connect to your system, and then you will install the BOA SDK. So the SDK will be sit here. It talks to both BOA server and the applications, so running on the computing environment. This is the overall structure of this BOA. And then this next chart, this one shows the role of those different components with the softwares required and what you would typically do with those different components here. So first you have a BOA server. On that server, you need to install the BOA software. What it does is it can manage and monitor the BOA services through command line. So you can those software are packaged in in Docker containers. So it can be managed with Docker Compose, those commands to start the service and to configure the service. Also, there's a LSF component within this BOA software. So you can monitor the jobs on that server. But one thing to keep in mind is that this LSF from the BOA server, it's just manage those internal BOA jobs. So it does nothing to do with the computing environment where you may have another job scheduling running. So this LSF is not talking to the external computing environment. It's just internally sit there to manage those jobs coming from the Docker containers. And then you have a BOA client. So in this client, you need to install BOA SDK, and you run your jobs from here. So this one, it does those orchestration between the BOA server and the computing environment. The communication between those BOA client and the BOA server is very minimal. All it communicates is your application's output numbers and your design variables. So normally the number of design variables for the optimization problems is not that big. Well, some may be in their hundreds, very few maybe in their thousands, but mostly where the BOA would shine is close. It's like below 100, like 10, 20, or 5 in this kind of range. This is not the total number of input to your application. It's just the set of design variables you want to vary in order to find the optimal solutions. So typically, this is not a big amount. So it's not like this parallel computing when you do a lot of communications. And then so you have your laptop or desktop where you can install your web browser. So you can manage or monitor the BOA servers. You can also manage or monitor your own BOA jobs through this web interface. So again, this is a logical view of those components. If on any one of those servers, the moment you install the SDK, that node becomes a BOA client, then you can run BOA jobs there. So you can install the SDK on your laptop as well. So make it a BOA client. So the simplest case for people to try this BOA is to install SDK on the laptop and then access BOA services outside. So that's a architectural structure. Now we come to this interface functions. People often wondering, people have some early experience, or they are trying to use this one. The first question people would ask is, how am I going to write my functions which will make the connections between my application and the BOA server? So those following slides will be focused on this one. A BOA job script is pretty simple here. This one shows the skeleton of the BOA job. So first, you need to import your BOA SDK, and then you create an instance of the BOA. And then in your this script, you would definitely define your function to be optimized. So in many real world application case, this function is just a wrapper of your application. So your real world application can do various kind of those designing, or it may generate multiple outputs. But in order to be able to use BOA to help come up with those uh, uh, recommendations with sampling points, you need to define, if it's not defined, you need to define a fitness function or a scoring function. Here, we call it objective function. So this function, what it does is takes some input, which is a Python list, and then comes up with a single score. So this single score is going to be used by BOA to do its optimization work. So you need to have your function, and then there's a configuration part. This is a Python dictionary. Its purpose is to serve the BOA server. So the BOA server may have some parameters you want to fit in, such as which acquisition function you want to use, the kernels, and some balance tuning between the exploration and the exploitation. So all those parameters are included in this dictionary. And in many cases, you don't need to change many of them. So the default works good there. So those two pieces is the ones which everyone is going to need to write to be able to make use. And then the following steps is pretty much standard. You register your account, you log into the system, you log into the BOA server system, you get a token, and then you create your experiment object. So you can run your optimization. So after it's created, then you start this BOA run API to start this whole optimization process. So once this API started, well, look, so for this API, you need to have your function definition, and also you specify the number of iterations you want to do. And this explain is, do you want to explain this to this feature importance of its extra capability in addition to the optimization itself. So once this process is started, it will run to this number of steps, and then finish the run, then you can collect your results here. So to start this process, you just issue this Python command from your BOA client. So if you want to have more control of your iterations, instead of letting this BOA run API to taking care of that, you can use another pair of API functions, which is the next parameter set and also the new observations. So that you can control the number of iterations. Manually control, say, I want to do one more iteration and see what happens, what I get. So you can do it with this set of APIs. The objective function, like I mentioned before, it's to real applications like your open form or your some those scientific and engineering workloads. This is very likely your wrapper. So, but the function by itself, it takes those inputs as the Python list and returns a single value. All those parameters are floating point numbers. So that's something to keep in mind when you are trying to do some like those shell parameter passing, because those are strings. So need to be careful when you do these patterns. You want to convert them to the appropriate data types here. So this function the simplest case, it can be analytic functions like the camelback example, which is shipped with the BOA SDK. And it can also be some training data. So in this case, we can call it a lookup table so that the problem you're trying to optimize, you have those like data points already. It's just too many. You want to find out the maximum of that. So you can have that kind of object function as well. And also it can be a wrapper for HPC simulations. So in that case, this object function needs to take care of the HPC or other scientific calculations, need to take care of its input and output and to come up with a fitness function. So here's the simplest case of this analytic form. It's just just a few lines of Python code. So this is a two-variable, it's two-dimensional camelback function. So in this case, the moment you run this Python job like Python myBOA.py, the BOA optimization work will be done on the BOA server. The calculation will be done on the BOA client. So it will not use, like if you have any extra HPC clusters, it's not going to be scheduled there. So this is an example of how you can use a lookup table as your objective function. The advantage of using lookup table is, well, if your table size is not huge, say, well, 1,000 or even tens of thousands or even millions there, it's not that difficult to get the global maximum or minimum by just a grid search there. So that means those kind of function is a good candidate for testing, for evaluating your algorithm or your parameter setups there, because you know what the maximum would be, you know what the minimum you're searching for would be. So this is a good value, but in reality, maybe the function you're trying to optimize, you don't know the solutions yet there. So that's a difference there. So you basically there are so many ways there. People use file IO to do those, and well, this is using the pandas package. So you read the data, and then the moment you want to get the particular column, you use those data frame function to locate the row which you want to retrieve by looking at the input values and compare the input values. This is another example, which is, well, I show it here because it is a totally different category. And this one would be very close to what people would be using in reality. So this example is trying to run the stream memory bandwidth benchmark. We know the stream memory bandwidth benchmark, it has those four metrics, but here, like copy, add, sum, and triad, we'll use a triad as example. And also for this stream benchmark, there are two, well, people may have more, but two basic input parameters is the matrix size and the offset. So here we use BOA to illustrate how you can get those stream benchmark optimized with the particular array size and the offset. So here again, the function takes input and return a single point here. So we will launch this sub process call. First, we get some input values, because the input values are coming back from the shell script, this one from the external process, our string. So we need to, in order to fit to this one, we need to convert those floating point numbers to string so that it can be passed to the external shell script, which we call compile and run. So this script, compile and run .shell, will decide where to run the application workloads. This is what that shell script looks like. It's pretty simple. Takes those two parameters and then compile the stream from the source on the fly, because we want to put those array size and the offset into the binary, and then we set up some environment and run the job, and we simply do a grep command to catch the triad number and echo it back to that objective function. In reality, people may use some like job schedulers to do those. The flexibility of the BOA allows people to do all those different kind of scenarios here. So you can install your BOA SDK to your front end or to your compute nodes or to some global file system, which is easily accessible. So we covered that objective function. Now this is for the BOA server itself. This is what those dictionary look like there. So you give a name, and then this domain is something which is depending on your design parameter space. So your input values of your optimization problem could be continuous domain. So in that case, you need to specify the minimum and maximum of each dimension. You can be those discrete domain. So in this case, in addition to the minimum and maximum of each input parameter, you also specify the step length to use. And there's also a pure domain upload. So in the lookup table case, you have pre-set up input values you want to search over. So those are three categories, which I will be showing in the next slides. But here, so you need to also the other parameters. There's like a model, which model you can use, and for those Gaussian processes, you can specify the kernel functions, and whether you want to scale your Y value or your input X values, and your optimization type is that max or min. So I'm not distinguishing myself in those, but it can be max or min. And then the initialization, you can use random to start your initialization, or you can use some known values to start your initialization here. And also there's a very important parameter, which is the seed. You know, this is a technique based on this machine learning. So the randomness is built in there, and that's the purpose of those things there is to get this random behavior. So if you want to see reproducible results, this is pretty good for debugging, to performance tuning, to understand some parameters. You want to have a fixed seed so that you get reproducible runs every single time. So those are these three different types of input parameters the current release of BOA can handle. I just mentioned a moment ago. So there's the bounds, grids, and domain lists. So you cannot mix them in one optimization problem. So your problem can be either one of them. It cannot be a mix. So in the following, I'm going to show a use case which I did to see how BOA performs against those grid search and random search. So the problem is application performance optimization. This is from the spec 2000 application. The application name is AMMP. So what this simulation does is this is to help design new processors, which would optimize which would get you the best performance of those set of applications. So in this case, it's to get the best performance of AMMP. So the microprocessor parameters, there are 13 of them. It's on the registers, the cache size, latencies, various parameters. So the purpose is to see what combinations of those particular parameters would give you the best yield. So this is the data is available from the Duke website, and there's a total of 4,000 total simulations. And the performance metric is the billions of instructions per second. The data has other parameters as well, like the power consumptions as well. So if interested, people can do that kind of research as well. So here are those 13 input parameters. This number of values for each one of them, and their range and increment. Some are regularly incremented there, some are not, like not equal distance. So it's so you in this case you cannot use this continuous or the grid. The way to use is to use this domain list. So here's a sample of those data, what they look like. It has a total of 4,000 rows. And here's a plot of this raw data. Now this is a 13-dimensional problem, but we just plot them as 2 dimensions. So it's Y and everything else. We can tell that the Y is the bits number. So the target is to find out among those 4,000 data points, which one has the maximum performance. So we've labeled them as a red cross here. So the target of this BOA optimization is to find out this data point in as few as possible number of iterations. So as I mentioned, this optimization is random in nature. So that also means if you do a single run, you get some number. That number does not tell you that much. Well, it does tell you very much, but you cannot say, well, this is what I get using this algorithm. Because you know, when you run it next time, you would get a totally different results here. So what's meaningful is to run them multiple times and get some statistical meaning. So in order to do that, I run this BOA job 200 times, and each time I set a different random number generation seed there. So the initialization sequence is guaranteed to be different from run to run. And this chart shows the median case of this optimization. So it's not the best, not the worst. It's a median out of the 200 runs. The black dash shows a true minimum, and the green line shows how BOA converges as the iteration goes on. And the red cross is the actual BOA sampling points for each iteration. So the green line is just the historical best of those red crosses here. So even we can see first of all, the BOA comes to this global optimal pretty quickly. So in about 25 iterations. And after that, it still wanders about. So it still goes on because we set the number of budget to be 100. So it will finish that 100 iterations, even though it's found the best solution as early as in the 25th there. And this is a comparison between the grid search and the random search with BOA. So again, this black dash is a true maximum, and the blue is a grid search. So grid search means we look from the very first data and compare them one by one, and then so if you search through the whole space, you get a solution, which is this blue line. And the random search is you randomly pick up some number every time, and then at the end of this run, you have this curve here. So we can tell the BOA is so much better in terms of this convergence. And again, this this grid search is just a one-time run because it doesn't change from run to run. But the random search, it does change. So this is the comparison between the median of BOA and the median of the random search. And this is a summary table of those studies. So it's mostly comparing between BOA and random search. This means the minimum number of iterations to get to the global max, and the maximum number of iterations takes to find the global and the mean, median, and standard deviation. So we can tell from those two comparisons, the BOA outperforms the random search in orders of magnitudes better here. And also, so it's not better in terms of those median and mean and max. It's also, well, of course, because if you are good in those metric, you're good in those standard deviation as well. So it's a standard deviation is very small. That means when we run this experiment, we are very likely to get the job done with those median number of iterations. So the improvement can be in like 100, like this one, the number of iterations it takes comparing with grid search is 138 times. So that's a huge save in the computing resource. And this one just shows the numbers up here. We just use the Gaussian distribution of those numbers. So we plot them here. So the blue line is the BOA. This orange is the random search. So we can tell the random search, it takes much longer of iterations to get those maximum average. And also the standard deviation is very, very wide there. So that means you can take, big chance of getting the iteration, getting job done in up to those number of iterations. So thank you so much for the listening to this session. So I don't know how much time left, but please, if you have any questions, can ask, or I have a slides upload to the Open Power website. So if you are interested, you can download the slides there.
Any questions? You can unmute yourself if you want to, or you can type them in the chat, whatever you prefer. Okay. Thank you, Xinghong. And yes, thank you for already uploading your slides. The recording should be available shortly, so people can also see that afterwards.
Okay, thank you very much for hosting.
Thank you.
Okay, thank you. Bye.